Hello friends, welcome to the session that is continuation of parallel connection. Then I discussed about what is unequal current sharing due to unequal static VA characteristics. Because of that, string efficiency is reducing. Then for remedy for this problem is, if it is operated for DC circuit, we can connect one equal resistance in series with each SCR if it is operated for DC supply. Then what is that resistance equal to? That resistance equal to VT1 minus VT2 by I2 minus I1, that we are getting. But if the same circuit is operated for AC circuit, AC supply means here I am giving for DC. If it is operated for AC circuit, if the thyristor is operating for AC circuit, now what you can do? A center tapped reactor is connected. A center tapped reactor is connected. The remedy for this problem is, for AC circuit, a center tap reactor is connected. Then how to connect the center tap reactor is like this. We can make the connection. A center tap reactor is connected. Let us two thyristors connected with the center tapped arrangement. Let this is L1 and this is L2, where L1 equal to L2 equal to L, consider, and these two coils are connected in series opposition. Connected in series opposition. It is connected in series opposition. And this is AC supply we are giving. This is the AC supply connected in series opposition. Now the question is, how this center tapped reactor equalize the current sharing? That I want to explain. How this center tapped reactor equalize the current sharing. Okay. For example, let us assume that initially I will explain both the currents are equal. Later on I will explain if the currents are unequal, how it is equalized. Okay. Let this current is T1 carrying the current of 100 amperes and T2 is also carrying the current of 100 amperes. Initially it is equal, assume that. Because of 100 amperes of current, let the voltage produced in a coil 1 is 10 volts. We know that if any coil, for any coil, if you apply the AC supply, then how to define I equal to V minus E by R. If any coil, if you supply with DC means, how to define I equal to V by R. If any coil carrying the alternating current means, there is an induced EMF. That induced EMF is called statically induced EMF. Because according to Faraday's law, if the conductors are stationary, flux is variable. Because of alternating current, we are getting alternating flux now. Conductors are stationary, flux is variable. Whatever the EMF is induced, that EMF is called statically induced EMF. But here we are giving DC supply. Constant supply means current is constant. If the current is constant means flux is constant. Conductor is stationary, flux is also constant. Is there any Faraday's law? No. There is no induced EMF. That's why we take I equal to V by R. That means, if any alternating current is passing through the L1 coil, let us assume that there is induced EMF of 10 volts. That induced EMF is called statically induced EMF. If the conductors are stationary, flux is variable, induced EMF is called statically induced EMF. That in detail that you know in other subjects, that is electrical missions. If the conductors are variable, flux is stationary, whatever the EMF is induced, that is called dynamically induced EMF. That concept that mainly we are using in DC generator. Statically induced EMF concept we are using in transformer. Okay. That fundamentals you know. Okay. Then this 100 amperes of current is flowing through the L1 coil. Let us assume that 10 volts is produced. Then this 100 amperes is flowing through the L2 coil, then 10 volts is produced because L1 equal to L2 equal to L. Then these two are connected in series opposition, then resultant voltage equal to, let you take E1 minus E2, that equal to 0 volts. Then this is 100 amperes, this is 100 amperes, means this is 200 amperes, then output is also 200 amperes, then in entering current and leaving currents are same, that KCL will be satisfied. Okay. This is happening if the current sharings are equal. If the current sharings are unequal, we want to equalize the current sharing by using reactor. How this reactor is equalizing the current sharing, that you will see. Okay. How the reactor is equalizing the current sharing. For example, let two thyristors are connected in parallel. Two thyristors are connected in parallel. Okay. Two thyristors are connected in parallel. To equalize this current sharing, we are using one center tap reactor. Let this is L1, this is L2. L1 equal to L2 equal to L. That means let this carrying the current of 120 amperes and this carrying the current of 80 amperes. This is 200 amperes and this must be equal to 200 amperes. Okay. Because of 120 amperes are passing through the L1 coil, let the voltage induced in the L1 coil is 12 volts. Because of 80 amperes is passing through the LT coil, then voltage induced in the L2 coil is 8 volts. Then what is the resultant voltage? 12 minus 8, how much? 4 volts. Is it resultant voltage is 0 here? No. But in this case, resultant voltage is 0 now. If this resultant voltage is not 0, according to Lenz's law, always statically induced EMF opposes the cause. Response opposes the cause. Na? Why am I applying Lenz's law here? This I am applying the Lenz's law. I am applying Lenz's law. Why I am applying Lenz's law means what type of induced EMF? Statically induced EMF. The direction of statically induced EMF is determined by using Lenz's law. The direction of dynamically induced EMF is determined by using Fleming's right hand rule. Fleming's right hand rule. But it is the statically induced EMF now. That's why I am using the Lenz's law. Then according to Lenz's law, always this response opposes the cause. Who is the cause? Difference of current is the cause. Who is the response? 4 volts is response. Up to what time it will oppose? Up to induced EMF becomes 0. When the induced EMF becomes 0, if this current sharing becomes equalized like this, but it is not exactly equal. There is some minimum EMF, no doubt at all, but it will reduce the current difference. That's why in this circuit, current is equalized according to which law? Lenz's law. That means in this circuit, current is equalized. Current is equalized. Current is equalized according to which one? Lenz's law. Current is equalized according to Lenz's law. Understood? Response opposes the cause. Who is the cause? Difference of current. Who is the response? Voltage. Up to what time the response opposes the cause? Up to the response will become 0. When the response becomes 0, then cause becomes 0. Who is the cause? Difference. Whenever difference of current is 0 means there is no difference of current, means current sharings are equal. This about the DC circuit, this for AC circuit. Sir, can you use this reactor for DC means? No, this cannot work DC. The reason is this one. For DC circuit, there is no induced EMF. That's why I am using resistor. For AC circuit, we are using the reactor. This is the equalization of current sharing for this, but it is not exact equalization. This is approximate equalization. This is one cause and this is one remedy. This is cause, this is remedy. That you know. This for AC circuit. Concentrate this one. This you know. this parallel connection itself. This case 2. Cause. What is the cause for unequal current sharing? Unequal current sharing due to unequal dynamic characteristics. Unequal current sharing. Unequal current sharing due to unequal dynamic characteristics. Unequal dynamic characteristics. Unequal dynamic characteristics. Then unequal current sharing due to unequal dynamic characteristics. That's what happening. That you will see. How unequal current sharing exists due to unequal dynamic characteristics. For example, let us assume that two thyristors are connected in parallel. Two thyristors are connected in parallel. Okay. Two thyristors are connected in parallel. Let this is T1, this is T2. We are selecting SCRs with the same rating and same specifications. Even though SCRs with the same rating and same specifications, practically they don't have same dynamic characteristics. The reason you know, because of unequal charge distribution. Let the turn on time of T1 is 20 microseconds. Let the turn on time of T2 is 30 microseconds. Let us assume that. Okay. Now the rating of this SCR is 100 amperes and rating of this SCR is also 100 amperes. Let this is 200 amperes. This also 200 amperes. But I am assuming that both the SCRs are having same rating. That's why both the SCRs are having same turn on time. With that assumption, I will trigger both the SCRs at a time. Triggered at a time. Both the SCRs are triggered at a time. Tell me, if both the SCRs are triggered at a time, what happens? The thyristor which is less turn on time, that thyristor will turn on first. Na? Later. First T1 is on, but T2 will not on. Before turn on of T2, the current through T1 is how much? Plus 100. Total is 200 amperes is flowing. This current is also flowing here. 200. But we already given triggering to T2 also. But before turn on of T2, the current through the T1 is 300 amperes. No doubt at all. After 10 microseconds, means at 30 microseconds of time, if T2 is on, no problem, but T1 will not be damaged. Then the thyristor will be damaged. If high currents are exist for long time, then thyristor will be damaged. Within small time, it cannot be damaged. If the same current is exist for long time, then more time, then thyristor will be damaged. Na? But after 10 microseconds, means at 30 microseconds, if T2 is also on, no problem. But once the T1 is on, even though triggering pulse is given to T2, then T2 will not be on. The reason is this one. Okay. Whenever T1 is on, this is T1 is on. Before turn on of T1 and T2, both are under off state. Na? Let the forward blocking volt, we are applying 100 volts. This is 100 volts and this is also 100 volts. Okay. Now, for both the SCRs, I given triggering pulse. Now T1 is on first time because of less on. Then still T2 is not on. But you given already triggering pulse. But once T1 is on, the voltage across T2 is voltage across T1. Once the SCR is conducting, it may be nearly equal to 1.5 to 2 volts, 1.5 volts. Then even though triggering pulse is given to T2, but SCR will not turn on, T2 will not turn on, because once the T1 is on, voltage across T2 is less than finger voltage. That is the problem. That means if you give the triggering pulse for both the SCRs at a time, because of unequal dynamic characteristics, one SCR will turn on first, the another SCR will not on. Once the another SCR will not on, the total current is passing through the one SCR, then SCR may be damaged. Okay. After some time, then T2 will not on now, because the voltage across T2 is less than the finger voltage if T1 is on, because these two are parallel. This voltage only will appear across this one. Okay. Continuously 200 amperes of current is passing through T1 greater than rating current, then T1 will be damaged. Now voltage across T1 is supply voltage. Now voltage across T2 is supply voltage. Now this SCR will be triggered. Now the total current is passing through T2, then T2 also damaged. Like this total string may be damaged. That is the problem with the unequal current sharing due to unequal dynamic characteristics. That means due to unequal dynamic characteristics in parallel connection, the total string may be damaged. The total string may be damaged. Okay. That means in this, due to this, the total string may be damaged. The total string may be damaged. String may be damaged. Then what is the remedy for this problem? What is the remedy for this problem? You tell me. The remedy for this problem is we can trigger the SCRs in such a way that both the SCRs turn on at a time. Then only this problem will be eliminated. The remedy for this problem is synchronized triggering. Synchronized triggering. The remedy for this problem is synchronized triggering. We can trigger the thyristors in such a way that both the SCRs will turn on at a time. Sir, how it is possible? Yes. Don't think like this. Because of both the SCRs are same rating, that's why both are having same turn on time, that's why don't give triggering pulse at a time. Like that don't think. The turn on time is mentioned in the data sheet. According to data sheet, we can design the trigger circuit, then we can make the trigger circuit in such a way that both the SCRs will turn on at a time. For that what you can do means, this I am telling that how many microseconds turn on time? 20 microseconds. Then what we can do means, the SCR which is having the large turn on time, for that thyristor, we can give the first to triggering. First apply the triggering. Then first I will give the triggering pulse to 30 microseconds. But for turn on of this one it takes 30 microseconds now. For turn on of this one it takes 20 microseconds now. Then after 10 microseconds, you give the triggering pulse to T1. For the SCR which is having the large turn on time, first you can trigger that one. All these are, it's not a manual operation. Just like you write one program using microcontroller or microprocessor, then automatically triggering pulses are applied. First I will give the triggering pulse. Let T equal to 0, this is triggered. From 0 to 30 microseconds. For turn on of this one, it takes 30 microseconds. Then I will trigger this thyristor at T equal to 10 microseconds. Then from 10 to 20, it will, that means 0 to 30 microseconds, 10 to 20, at T equal 10 microseconds. Then already here 10 microseconds is completed now. Then both the thyristors will turn on at 30 microseconds. Understood or not? First you give the triggering pulse to the thyristor which is having the high turn on time. Understood? Then you give the triggering pulse to less turn on time. Then we can make both the thyristors are turn on at 30 microseconds. If you give triggering at T equal 0, then it takes 0 to 30 microseconds it takes. Then after T equal to 10 microseconds, then it is also completed 10 microseconds. Then how many microseconds it takes? 20 microseconds. Then at T equal 10 microseconds we are doing. Then how many microseconds it takes? 20 microseconds. Then both the thyristors will turn on at a time. That means, what do you mean by synchronized triggering means? We can make the triggering in such a way that both the SCRs are turned on at a time. How it is possible means, we can trigger the thyristor with a large turn on time is first. Then we can give the triggering pulses. Then we can give the triggering pulse to the thyristor which is having the less turn on time. Like that we can make the triggering. Then we can make the both the thyristors are turn on at a time. This is the cause and this is the remedy. Then case 3. Case 3. Then what about case 3 means? That is cause. What is the cause? Unequal current sharing. Unequal current sharing. Unequal current sharing due to unsymmetrical mounting. Unsymmetrical mounting. Unequal current sharing due to unsymmetrical mounting. What do you mean by this? What do you mean by unsymmetrical mounting? Let us assume that 3 thyristors are connected in parallel. Let us assume that 3 thyristors are connected in parallel. Okay. 3 thyristors are connected in parallel. Okay. I am connecting like this. And mounted like this. This type of mounting is called unsymmetrical mounting. That this is T1 thyristor, this is T2 thyristor, this is T3 thyristor. And these 3 thyristors connected in parallel. This type of mounting is called unsymmetrical mounting. Let this carrying the current of 100 amperes, this carrying the current of 100 ampere, and this carrying the current of 100 amperes. Okay. Then total is 300 amperes. And total is 300 amperes. Entering current and leaving currents must be equal, 300 amperes. Now, if this thyristor carrying the current means, because of this conductor carrying the current means, this, if any conductor carries the current, around the conductor a magnetic field is produced. That magnetic field is represented by imaginary lines. Those imaginary lines are nothing but a flux lines. Now, this conductor produces the flux. Practically these are placed very close. This conductor produces the flux means this flux links with this conductor. And this conductor also produces the flux. And this conductor also, this thyristor is also, means this conductor also produces the flux. And this links with this flux, links with this conductor. Similarly, this also produces, links with this conductor. And this also produces, this links with this conductor. Tell me, for which thyristor more flux linkage? This is for more flux linkage. More flux linkage. Okay. Because of more flux linkage with the middle conductor, more flux linkage with the middle SCR. Middle SCR. Now what happened? We know that flux linkage equal to n pi na. Flux linkage psi equal to n pi. Psi equal to n pi. Then we can define L equal to n pi by I na. That is psi by I. If the flux linkage is increases, what about inductance? Increases. If the inductance is increases, what the reactance offered? Increases. What the impedance of that offered by that thyristor? Increases. In this path, if the impedance is increases, then what is the current? Then current is reduces. If the current is reduces means, let for example it becomes 80 amperes. If it is becomes 80 amperes means, to satisfy KCL, these currents are increases. That means then current sharing becomes unequal. This is the cause. Due to unequal current sharing due to unsymmetrical mounting. Because of this unsymmetrical mounting, the current sharing becomes unequal. Then what is the remedy for this problem? What is the remedy for this problem? What is the remedy for this problem? The remedy for this problem is symmetrical mounting. Symmetrical mounting. Okay. The remedy for this problem is symmetrical mounting. Symmetrical mounting means this is also parallel connection, but we can mount the thyristors like this. This is T1, this is T2, This is T3. Therefore, therefore current sharing becomes unequal here. Current sharing becomes unequal. Here you can note this one. Current sharing becomes unequal. Okay, unequal. Then, if it is a symmetrical mounting, what happened? This type of mounting is called symmetrical mounting. Here also flux is produced. Here also flux is produced. But what happened? This flux links with this thyristor and this flux links with this thyristor. And this flux is linkage and this flux is linkage. Okay. And this flux links with the thyristor and this flux links with this thyristor. Therefore, for all the thyristors, same flux linkage, and same current sharing. Okay, this type is called mounting, symmetrical mounting. This also parallel, this is also parallel. But I am telling that instead of mounting like this, you mount like this, then that current distribution, whatever the problem is unequal current sharing, that can be overcome. Because for all the thyristors, same flux linkage is possible. The same concept we are using even in the transmission system also. This type of mounting is called transposing of transmission lines, symmetrical mounting, that we are doing. Here also same concept we are applying. Okay. Then this is the remedy. Case 2, cause, remedy is synchronized triggering. Case 3, cause is unequal current sharing due to unsymmetrical mounting. This is nothing but unsymmetrical mounting. This mounting is nothing but this one is unsymmetrical mounting. Then what is the remedy for this one? Symmetrical mounting. Remedy for this one is symmetrical mounting. If you mount like this, then for all the thyristors, same flux linkage and same current sharing. Okay, this about in detail about the parallel connection of thyristor. That is concentrate. Yes, clear? Okay, with this in detail about series and parallel connection is completed. With this knowledge, based on the series and parallel connection, whatever the concepts I discussed, based on that we can solve some classroom workbook questions. Then you get idea how the questions are framing in competitive exams. Okay, clear? Concentrate, all of you take the workbook. See the chapter 2 itself, thyristor, that is SCR concept. Yes, this thyristor, that is SCR concept itself. In the topic 1, I discussed in the classroom workbook based on the switch concept, that is switch concept. In topic 2, I discussed about diode concept. Topic 2, I discussed about diode concept. In topic 3, I discussed about static VI characteristics and construction based questions. In construction based questions, I discussed topic 3. Under topic 4, after that construction and static VI characteristics in the thyristor itself, I discussed about in topic 4, that is protection circuit, and gate characteristics that I discussed, topic 4 that I discussed. They will see the another topic, that is the topic is series and parallel connection of SCR. That is topic is series and parallel connection of SCRs. Okay. A series and parallel connection. Based on this, we will see series and parallel connection. Parallel connection. Okay. Based on this topic, see the question number 1, all of you. See the classroom workbook, and topic is series and parallel connection. Based on this topic, parallel connection of SCR. See the first question. Concentrate. Okay. Number of thyristors, each with rating of 500 volts, 75 amperes, required in each branch of a series parallel combination for a circuit with a total voltage and current ratings of 7.5 kV and 1 kiloampere respectively. If the device derating factor is 14%, then what is the number of thyristors in series and parallel branch respectively? That means you want to calculate number of thyristors in series connection and the number of thyristors in a parallel connection. Number of thyristors in a series connection and number of thyristors in a parallel connection. Yes? Given that, see the first one. What is the solution for this problem? What it is given? Individual voltage ratings and ratings of circuit voltage and current ratings is given. What the string voltage is given? 7.5 kV. What the string current is given? How much string current is given? String current is given as 1 kiloampere. 1 kiloampere. Individual voltage rating is given as 500 volts. Individual current rating is given as 75 amperes. Simply you remember like this type of problem. High voltages, high currents you take string voltage, string current. Low voltage and low currents you take individual voltage and individual currents. What the derating factor? Derating factor DRF equal to 14%. Then it is equal to 0.14. Derating factor equal to 0.14. Then you calculate number of series connected SCRs and number of parallel connected SCRs. You calculate number of series connected SCRs and number of parallel connected SCRs. Then first you tell me what is string efficiency? String efficiency equal to 1 minus derating factor. This you know. Then string efficiency equal to 1 minus 0.14. Then how much you get? 0.86. String efficiency equal to, you are getting 0.86. Now I want to calculate series connected SCRs. Series connected SCRs. Want to calculate series connected SCRs. For series connected SCR, how to define string efficiency? Voltage across whole string by number of series connected SCRs into individual voltage rating of each SCR. This formula is given. Voltage across whole string by number of series connected SCRs into individual voltage rating of each SCR. Then what is the string efficiency? 0.86. Then what is the total string voltage? String voltage equal to 7.5 kV. 7.5 into 10 cube. Okay. Then what is the number of series connected SCRs you want to calculate? What is the individual voltage rating of each SCR? 500 volts. Now from this, you simplify this, what you can get? NS is nearly equal to 18 thyristors you can get. 18 thyristors. Okay. Then for parallel connection, you do for parallel connection. For parallel connection, you want to calculate number of thyristors in a parallel connection. For parallel connection means, then what is the string efficiency equal to? IS by NP into I1. Okay. Then this is 0.86. What is the string current it is given? Tell me. 1 kiloampere. 1 kiloampere means 1000 ampere. NP want to calculate. Individual current rating is how much? 75. Then you simplify this. What you get? The number of parallel connected SCR. This we can get NP equal to 16. This is number of parallel connected SCRs and this is number of series connected SCRs. Then you take number of series connected SCRs is 80. Then in the given options, which is correct? Yes. In the problem, answer is option A. That is simple. Note down, quick. Direct formula. Series connected efficiency, parallel connected efficiency formulas that I given already. From that we are calculating number of series and parallel connected SCRs. Okay. See the question number 2. Second question. What is the solution for this problem? SCRs with a rating of 1000 volts and 200 amperes are available to be used in a string to handle 6 kV and 1 kiloampere. Calculate number of series and parallel unit required in case derating factor is 0.1. Okay. Then tell me what the string voltage it is given? Quick. 6 kV. What a string current it is given? String current is how much? 1 kiloampere. String current is 1 kiloampere. Yes. What is the individual voltage rating of each SCR? V1 equal to 1000 volts. Individual voltage rating is 1000 volts. What is the individual current rating of each SCR? 200 amperes. What it is given? Derating factor. How much? 0.1. Then you calculate number of series and parallel connected SCRs. How many number of series connected SCRs? How many number of parallel connected SCRs? Okay. First you define string efficiency. String efficiency equal to 1 minus derating factor na. Then 1 minus 0.1 na. Then how much you get? 0.9. Then first I want to calculate for series connected SCRs. For series connected SCRs. Then how to define string efficiency? Vs by Ns into V1. Then number of series connected SCR. Vs. Total string voltage how much? 6000. 6000 by. You want to define what is the string efficiency? 0.9. What is V1 we are giving? V1 is given as 1000. Then how much number of series connected SCRs you can get? 6 by 0.9. That is 60 by 9. 60 by 9 means what you get? 6 point. Okay. 6 point. How much you get? 4 like that. Nearly you can 6.4. Then the number of series connected SCRs equal to 7. Nearly equal to 7. This you take. Point to remember, even 6.1 you can get, you take 7. It is not according to mathematics, according to technically. That I told now, in the selection of a string, you give the preference to reliability. If you want to maintain high reliability means, you maintain more number of SCRs na. That's why, even 6.1 is came, you take 7, don't take 6. Not according to mathematics, according to technically you consider. According technically you consider. Yeah, that is the number of series connected SCR. Okay. How many number of parallel connected SCR? If it is given that number of parallel connected SCR, that I want to calculate for parallel connection. For parallel connection. For parallel connection. How to write? For parallel connection means then what is the string efficiency for parallel connection? Is by Np into I1. Then from this what is Np equal to Is by eta I1. How many? What is the string current it is given? 200. Sorry. String current 1 kiloampere na, that is 1000. Then what is the string efficiency? 0.9. What is I1? String current is given 200. Then you can get number of parallel connected SCRs is 6 you can get. Like this we can solve. This number of series connected SCRs and number of parallel connected SCRs. This is question number 2. Yes. A thyristor string is made up of a number of SCRs connected in series and parallel. The string has voltage and current ratings of 11 kV and 4 kilovolts respectively. The voltage and current ratings of available SCRs are 1800 volts and 1000 amperes. For a string efficiency of 90%, calculate. First one is number of series and parallel connected SCRs. For these SCRs, maximum offstate blocking current is 12 milliamperes and reverse recovery charge is 25 microcoulombs. Determine the value of static equalizing resistance and dynamic equalizing capacitance. Yes, quick. What is the solution for this problem? Tell me. What is the string voltage it is given? High voltages you can take 11 kV. What is the string current it is given? String current is given as the voltage and current ratings 11 kV and 4 kiloamperes. 11 kV and 4 kiloamperes. This is 4000 amperes. That is 4 kiloamperes now. 4000 amperes. Then Vs is how much? 1800 volts. What is Is? Not Vs. This is V1. What is the individual current rating of each SCR? 1000 amperes. 1000 amperes. This is 4000 amperes. 4 kiloamperes now. 4000 amperes. Then what the string efficiency is given? String efficiency is 90%. That equal to 0.9. 90%, 0.9. First one. First question is number of series and parallel connected SCRs. How many number of series connected SCRs and how many number of parallel connected SCRs? First we will see for series. For series connection. For series means then eta equal to Vs by Ns into V1. From this V1 equal to what is the string voltage? 11,000. 11,000. What is the string efficiency? 0.9. What is V1? 1800. Then we can get number of series connected SCRs. Ns equal to then how many number of series connected SCRs we can get? 7 we can get. Nearly equal to 7. Then for parallel, we can do for parallel connection. Okay. For parallel. Then for parallel means, then what is the string efficiency? Eta equal to Is by Np into I1. Np into I1. From this Np equal to, what is the string current it is given? String current is how much? 4000. 4000. Efficiency 0.9. What is the individual current rating? What is the individual current rating? That is mentioned as 1000. Then you can get number of parallel connected SCRs. That you simplify, you can get number of parallel connected SCRs is 5. Okay, this is A. Then concentrate on question number B. You calculate static equalizing resistance and dynamic equalizing capacitance now. The maximum blocking current. The maximum blocking current is given as how much? IBMX. IBMX equal to how much? How much it is given? The maximum blocking current is 12 milliamperes. 12 milliamperes. Then the charge difference is how much it is given? The charge difference is given as how much? Yes, sir. The charge difference is 25 microcoulombs. 25 microcoulombs. Then static equalizing resistance R equal to static equalizing resistance. What is the formula? Ns into VBMX minus Vs by Ns minus 1 into delta IB. How many number of series connected SCR? 7. Maximum blocking means individual voltage rating of each SCR. How much? 1800 minus Vs 11,000 into 11,000. That is 7 minus 1 into delta IB. How much? 12 milliampere. 12 milliampere. Delta IB is 12 milliampere. IB maxima minus IB minima. IB minima is not given. You take only IB maxima. IB minima is 0. This we can get 22.22 kilo ohms. By simplifying this we can get. Then you want to calculate which one? Dynamic equalizing capacitance. Then what is the dynamic equalizing capacitance you tell me? Ns minus 1 into delta Q by Ns into VBMX minus Vs na. VBMX minus Vs na. Ns is 7 minus 1. It is also series connection only. 7 minus 1. What is the charge difference? 25 microcoulombs. 25 into 10 to the power of minus 6. 7 into VBMX is how much? Blocking voltage 1800. 1800 na minus Vs. String voltage is how much? 11 kV. That is 11,000. Then you simplify this. We can get capacitance equal to how much? 0.094 microfarads. these models we concentrate based on series and parallel connection. Then if any theory questions are framed, okay, then whatever the theory I given, based on that theory we can answer any question. Maximum up to now in competitive exam they are asked only for series connected SCRs and parallel connected SCRs. Then I extended this problem. They asked for what is the static equalizing resistance, apply this formula. If it is asked what is the dynamic equalizing capacitance, ask this one. This we can, like this we can. With this in detail about series and parallel connection is completed. Some classroom workbook questions based on series and parallel connection. 3 questions I solved. This is enough. Understood? Okay, note down this.